All right, so we're back at it again. Last time, or yesterday, we were working on the tokenizer, or just a language that looks like this. And we got it to where it can tokenize all of these tokens correctly. Today, I think we're going to work on parsing those tokens. I think just correctly. Like, we're not going to worry about building an AST or anything right now. And I did upload the repo to Codeberg. It's over here. So, and there will be a link in the description as well. So, yeah, let's try to write this parser. What do we call this? Nala. So, when I write parsers, I don't usually keep the like a list of the tokens. I just like tokenize on demand. So we'll keep a tokenizer. Let's call it key in the parser struct. They call it tokenizer, right? And then helper functions that we need is end of file. Yeah, we can just peek at the next token if it's the end of file token. Obviously, we're at the end of file. We can make an expect function procedure. I just can't do. And this will expect a token hive. Let's not make it this way for now. We'll just make a matches function because I don't know how I want to do error handling. No, we can just panic for now. So this expects a token. Maybe we'll allow people to put a message in here. I don't know how to do variadic args in Odin. And then I guess we do also need our matches. I think that we will do multiple returns here. We'll return the token. And I guess we've handled this differently too then. So we can match, we can expect. Yeah, I think that's all that we need. So, and this won't return anything. Right now, this basically is just going to validate, I guess, the input. All right, so let's go look at our sample. I guess this should be a top level statement, maybe. Top level. Maybe more. Maybe I should actually just call it a declaration. So a declaration looks like this. So we expect that keyword. Expect should probably also return the token. Yeah, this way we can expect an identifier and get the identifier back. And yeah, second part is an expression. And that's it. So what is an expression? I guess we'll just start at the top. So we'll start with an import expression. So if, let's make a peek. Switch on that then. So first we'll do our import expressions. Does expression, yeah, so we'll have to actually advance it then. Kind of getting ahead of myself here. Let's just move on to the import itself. So we never actually ate the import token, so we can expect it here. Then we can expect the left parentheses. We'll import expression, I guess. I don't know what to call that. And then we expect the right parentheses. This is. I wish there was a way to. Oh. In Odin, you can just append strings, can't you? Like by adding? Or is it, I'm thinking. Oh? If you concat, do you have to free it? They're not freeing it. Maybe I just use the temp allocator? And that sounds weird. Anyway, we'll just go with it. Getting used to Helix, so I don't really, I normally use Vim, so I don't know how to surround this string. And then I can So let's see if this works. Unexpected token, and then we will. Will Odin automatically turn that into a string? Guess we'll find out. Used to zig. Wait, what? This has to be marked as partial. Even with like the fallback case. Let's get rid of the message. I don't feel like doing that every time I expect. Oh yeah. That can still be file. Oh, it's not called tokenizer peak, it's called peak. Let's see. Tokenizer advance. No, it's just called next. So many typos. Maybe I should get an LSP if I'm gonna like mistype this much. Wait. I might be an idiot. Well, I definitely am. Did we not? Yeah, we never actually made the tokenizer peak on that procedure. Yeah. We're learning Odin here. Where was that? We might have forgotten to we couldn't have. What's it called? Oh, it just parsed this as an identifier, so we didn't actually do it right. We're so close. They call it cat. Cat to meat. Cat. So how do we get the enum variant to be a string? I guess we're just gonna format print it. %b. I think we finally got it. Unexpected token in expression keyword struct. So I don't know why it like took forever to quit out, but it looks like we got up to here, and that's because this isn't an expression. Does that take a long time to run again? Okay, it's whatever. Let's parse structs. What was a struct definition? Okay, so this is where I guess it gets a little bit interesting. Let's pretend there was no body. We just parse the last curly brace. So now we have to loop. We'll say while, or for, I guess, for not at end of file, and this is annoying. I want to match, but I just want the bool. Like, I don't actually want to take the token. No, we can just peek. Peek is not equal. So while we're not at the end of the file and we're not at the closing curly brace, we want to parse a struct field. What? And we can say found. If not found, we do. So if there's not a comma at the end of one of these, then we can just exit out, and then we expect the curly. So now we parse the struct fields. first expect an identifier. Then we expect a colon. And then we will do parse a type. Okay. Moving on to parse type. So what types are types? They're identifiers. I think the way I might do this is to just say parse expression here. Yeah. Yeah, we'll just parse expressions, and then later on, we'll validate if an expression is like a proper type or not. I don't know, we'll see if this works. I feel like it could be a lot to validate that, but we're just gonna push that to future me. So yeah, except for the fact that we don't know what kind of expression this is or this, this should work. So let's just do those and then see if we fail here. I wonder if instead of panicking, we should exit. Random thoughts. So first we'll do the slice. Case dot L bracket. Yeah, this is just a slice type. And if it's an identifier, we can just expect it. Okay, parse slice type. Expect the opening bracket. I think that's what we called it. So in theory, this could also be an array. So we have to see if peak does not equal R bracket, then we'll do a parse expression here. Then we can expect the R bracket. And then we can parse the expression afterwards. All right, that should do it. First struct definition, did I type it wrong? parse struct definition. Dot identifier. Cool. Why does that take so long to exit? So instead of panicking, let's just exit and see if it. Well, I don't know why panic is so slow. Anyways, this is working. We get up to the function keyword. So let's put this up here. Function keyword. We expect parenthesis. Then we have to do the same thing that we did for the slice, kind of. So if peak does not equal the right frame, then we'll parse args, function args. Excuse me. Function args p. And then we can expect the right parenthesis. And from here we can do parse block. We haven't defined yet usually how I program by pretending things exist that don't. But yeah, block will just be a list of statements inside of curly brackets, braces. So let's first do our parse function args. So we can say while again for for not is end of file, and peak does not equal reference. Parse function arg. No, let's just do it here. So what does a function argument look like? We expect an identifier. I guess this one doesn't have arguments, but this one does. So let's just go here. We expect to have an identifier. We expect a colon. And then we expect a type, but types are just expressions, so we'll parse an expression. Match on the comma. Yeah, I think we can choose P. How did we do it before? That should do it. So now we just need to do parse block, which is also here. So this is starting to become a pattern, but that's what parsing is like, at least with recursive descent parsers. So now we have to make this parse statement function. Procedure. Fortunately, I think that we have, like most cases, well, yeah, I guess not most. Anyway, doesn't matter. Parse statement. So here we also have to do a switch on the peak token. I guess that's to be partial. So we can do our let keyword. Unfortunately, we already actually have this written. It is just parse declaration, I think we called it. Declaration. Yeah. Ooh, this is interesting. So right now, this would get parsed as an identifier and then a block. How do we want to handle that? I don't particularly want to just like continue parsing. No. Yeah, until this fails when it gets to the comma and then say, oh, this block must be like a set of fields. But I also this is why most programming languages use commas, or not commas, semicolons. Because yeah, we can't even say that all structs are just an identifier, because this could just easily be like a standard.writer or something, right? So this actually has to be parsed as an expression. Like yeah. So we could enforce this. I think that's what we'll do for now. And then we'll just copy Zig. I don't feel like, I mean, not that it would be that hard. I think we can do this right now. And then when you have the dot, curly brace, that's how you do structs. Like a struct literal. I'll have to think more about how I actually want to parse this. Because I think I would prefer to be able to. Oh. What the heck? We just do this. Yeah. But for now, we're just going to do this. Where were we? Statements. So we have to switch up how we parse declarations because now there's an optional type that can be added. So where's our declaration? So we can do our if peak equals dot colon, and we expect the colon, and we can parse the type. There's an expression. Okay, so that should be fine. And then now we actually do have to run into the token, or like modify the tokenizer, because we could just look at this as two tokens, but then that would allow like dot space, which I don't like. So we actually have to add a new token that is these two characters. So where's our dot? Let's go over here and we'll say dot curly. We'll just call it. And then the way we do this is, where do we tokenize the dot? Here. We can do this, but instead of just returning the token, we change the state to be, just call it the dot state, and then continue. And then if we're in the dot state, this is not how we do it. How did we do the slash? Yeah, we had to check it. Here. Wait, the only reason I think we had to do it this way was because we were reading until the end of the line. Right. What kind of tokenizer functions do we have? Just peek in advance. think I was right the first time. So we eat the dot, set the state to the dot, and then continue. When we continue, we end up over here. We check if the next token after the dot is exactly the left curly. Eat it and change the token kind, and then return the token. And then if it wasn't a curly, we just return the token that it was, which is a dot. Now we just have to add the dot state. Unexpected token in expression dot curly. So is that what we'd expect? So we parse the function, we skip the comments, they get skipped in the tokenizer. We get here, it looks like we're able to parse the type you would expect, and now we get here, because this is not a valid expression, right? Go back to the parser and let's make it an expression. Curly, and we'll do parse stroke lit. So and this is going to be just about the same as parsing anything else that we've done. Stroke literal. So we expect the dot curly. And then here we expect a field initializer, maybe? And a field, I don't know. Oh. So it's just like when you go to the corner of the screens. Interesting. I want to turn that off. It happens a lot. I've never gone to the top left. Normally it happens when I switch monitors by going to the top right. Anyways, so and a field, yeah, so we get identifier colon expression comma. We have to do our comma check here. Expect an identifier. Expect a colon. Parse an expression. And that's it. So, oh, look, this is interesting. This array initialization is the same, or it's similar as this, right? So it's gonna parse this as this, an array type. So this should fail in by expecting a comma, or unexpected comma when it expected this, right? So let's see if we get there. This one I think is a little bit easier to fix. Oh, it panics again. Can we not get rid of the panic? Okay, yeah, let's do the format dot f unexpected token. Oh, we have to do that, bro. Oh no, yeah, we figured it out. It's with the percent fee, right? And then we can do os.exit. Yeah. Cool. So unexpected token, comma. Well, maybe this isn't as easy as I thought it was going to be. So we have a couple of cases, right? So we have let array equals this, that's valid. This is valid. And yeah, this is valid. If it gets here, it's going to still think that it's a type. Like we're going to be calling parse expression, which is going to fail because the next token is let. Again, this does mostly get solved with semicolons. Because if there's a semicolon at the end of this, then we can just see if there's a semicolon, and if there's not, then it must be a type, or like it must be an array type specifically. Yeah, the other thing that we can do is like, so far I've like in fact all non-expression statements, which we haven't even done expression statements, or really any statement except for the declaration statement, but they all start with a specific keyword. So you'll have like let, you have while, and you have if. If is a bit problematic because like I would like it to behave as an expression, but we haven't done that yet. Yeah, we have. Anyway, the reason I bring that up is because we can just check if the next token is a statement token, which would be one of those tokens. And if it is, well then that must be the end of this statement because a new statement is beginning. So we can use that kind of as the boundary. But if we do that, that means that we can't use ifs as expressions. Which I'm cool with for now. So let's make a list of our statement tokens. How do you erase working in Odin? Declare. Like, what if I don't? Do I have to type it? What? I guess I do. Maybe it has the underscore that it has. This is an array of token kinds. And we set keyword what? Let dot keyword while and dot keyword if. And then I think I still need to think about, like, because this is a statement, but it's also an expression. So if this was here like this, oops. It would actually parse it as this. An array, zero length array of whatever type this is. I'm going to refine this stuff later on, but for now I think we will add optional semicolons. So it will by default parse it like this. But if that's not what you want, just add a semicolon here. Which is kind of gross. That's what we're going to do though. That is disgusting. Okay, so anyway, token statements. Let's see if this compiles. It doesn't. Oh, question mark. Question mark can only be used in conjunction with compound literals. Oh, I'll look. Isn't... Oh, I see. There we go. Unexpected token in expression. Oh, look, that's actually happening here, I think. Yeah, because parsing the array, an empty array. So let's make our check for whether we're at a statement boundary. We'll call it so we take our peak token. And say for keyword token. What do we call this? Statement. In statement tokens. If token equals statement token, return true, return false. So how do we use this? Carefully. Where was our parse? Wait, our parse slice type? Yeah, I think we can more accurately call this parse array now. Maybe that's less accurate. I don't know if they're all the same because it's going to parse slices, slice types, array types, and array initializations. So we're going to ignore the array initialization. And we'll first So before we parse an expression, we have to say if we're not is statement. Let's call it statement boundary. Unexpected character. Semicolon, unexpected character. Right. So let's add this semicolon. Unexpected token in expression semicolon. So we did get here. Comment here. Maybe we can use new lines. So anyway, where were we? So we're getting this because we're not at a statement boundary. Oh, you know what we can do? We can just say that the semicolon is a statement boundary. And declarations. Yeah, so parse statement is going to eat the optional semicolon. Matches. So if there's a semicolon, it'll eat it. If not, doesn't matter. Keyword semicolon. Unexpected token in expression identifier. What identifier? Whoa, where's my bit set S line? Let's just print. Yeah, we're gonna print the tokenizer. The Lexine. Wait, can't we just not do this by value and it's or by reference? Oh, we actually need our token. This is the token kind. We'll just make another function for a peak token. Oh, tokenizer peak. Oh, just return the token, bro. So this will return the token. This will return. We could just use this, but most of the time we're not using this. The question is, does it let us do that? I think it's not. Oh. Maybe it was. Yeah, we can't. Unexpected. Oh, it's not in here. Statement. Oh, that's because it's a random thing. So in the default case, I guess we just parse an expression here then. Yeah, parse an expression. So if it's not a statement that we recognize, yeah. No, it should be fine. Well, yeah. Aha, unexpected token dot. That's what we were expecting. Right, because that is over here. So this is where we have to start implementing binary expressions. That's what this is. Those are fun. Let's save some of what we're doing here. What are we doing? Just like statement parsing. So, how are we doing the binary expressions? This is how I like to do them. We have our parser. We will have another private a couple things actually. So one is an infix operator. Actually, no, I think we're fine. We don't actually need that. A function for is infix. And it takes in a token, token kind. And it returns a BP and a bool. And a BP is a BP for binding power, which has a left, which will be U8, and a right, so U8. Let's just make a level function. Proceed. Correct myself every time if I can. Maybe I'll get it right eventually. Level, BP level. I hope that like Odin is. It doesn't matter if it does this at comp time or not. It's like not a crazy procedure. It would be cool if it does. So we'll do level, and this will return a BP. And then we also need associative. Say hi. Start low. Low equals U8 level times 2. I equals low plus 1. And then if it's left associative, return low high, high, no, else return low high. This just makes it a little bit easier to change the precedence, which doesn't have to happen often, and really just happens at comp time. But this way I don't get frustrated by that. So is a token an infix operator? Let's go look at our tokens. So switch. The kind. And I guess we have to do partial switch again. default, it is not an infix. So we have plus and dash. Which are, I think one other thing that we'll want actually is the infix operator. Maybe we can just use that instead of cool. I don't really like having an invalid infix operator. We're gonna just start with our like arithmetic operators. Star is gonna be multiply. Also, these obviously at the same level. This at a higher level. And slash is gonna be div the same level as yeah, so the whole reason I did the BP level function is because as I'm adding operators here, I'm gonna have to be like shifting these, and I don't want to have to keep figuring out what the left and right binding powers need to be for each of these. So yeah, and then let's add I really don't like invalid. Let's just return add, and then let's just also make a BP of 0, 0 be like invalid. Actually, it's kind of annoying, I'm not gonna lie. New idea. Here we can say infix top BP I wish I knew how to go up after I press Y or X and helix. Plus dash star slash And then here we can just return false. So let's start writing our parser for this. It should be up here with parse expression. And when I say up here, I said that while I was at the bottom of the file. Parse expression BP. So, and now I think that we should call this parse expression primary. And the way this works is we start with our left-hand side of a potentially binary expression. And we parse the primary expression. We say that our infix in our BP, and while for is infix key.p. And we return to left-hand side. So we parse left-hand side, and then afterwards we check if it's an infix operator. If it is, we also need to see if the binding power for the infix operator is greater than the minimum BP. Or I guess in this case we'll say if the binding power dot left is less than the minimum BP, then we have to break. The precedence has failed. Otherwise, we can advance. We can eat the operator. Wait, we don't actually have just a generic advance. We haven't had to use one. We can't expect because we don't know what it's what it actually is. Just do an advance here. Oh, we don't need it because we can just do tokenizer next. That's why I didn't do that. Tokenizer, tokenizer next. Yeah. And now what we do is we say right hand side is equal to the parse expression BP, but we use the right binding power of the infix operator that we just got. And then we make a new, technically we're not building expression trees or anything like that, like ASTs. So it is enough, I think, to, yeah, we're not actually, what am I doing? Assigning left-hand side, the left-hand side. We're not making expressions. Yep. That should do it. So to see if it does it, let's go back to our example. And right now, yeah, we haven't implemented that, but it's not actually that hard. We could just do, but let's do let sum equal like 1 plus 2. First, oh, we also need first expression. Get rid of it. First expression. Which is just going to be parse expression BP. Even 0. Key.peak, trying to use it like a method. Right, these are left associated. Let's just make this left and right. Everything's left associated for now. Okay, so it did get through it, right, and it fails on the dot, because that's still not, where are we? That's still not an operator that we have. And if we add, like, star 3, completely, right, it gets through. Technically, we're not able to see the order that it parses in, so we can probably do that by just printing where did it go for speedy? Format dot print up. So, and if we change this to be a star, this to be a plus, it should swap, right? Yeah. The multiplication happens before the add. It looks good. We'll see it better when we do have an AST or whatever we have to actually represent this. But for now, let's add a new operator, the member access. We'll call that. We don't need that anymore. So to add an op, we say case dot. This is actually, is this? Yeah, it is left associative as well. I don't know what its precedence should be. Like, I would think it should be high, right? Because if you wanted to say let x equal like yeah, you need this. The dot needs to be pretty high. set it to 10. Ah. So now we get up to this. Let's stop printing buttons. So we get up to the left parenthesis, which this is an operator. It has to get handled differently than other infix operators. It's actually not an infix operator, it's a postfix operator. Where should we parse postfix operators? Oh no. But let's do it up here. So there's going to be two postfix operators for now. One is the all operator, and the other will be index operator, or like array indexes. We can still use the same BPs, and the function can still look like this. And then this will be is postfix. So the one is a left parenthesis as a postfix operator, and then the left bracket. And these I think have pretty low precedence, so let's change this first. Yeah, these have. Oh, let's see. Nope, they have high precedence, but lower than the dot. I don't think we really use their the right-hand binding power for that either, but we'll see as we write that. I think that's right. Where's the expression BP? Where did you go? Over here. So this actually just has to become a forever loop. So if it's an infix, we can do this. Otherwise, we have to see if it's a postfix. If it is a postfix, we should continue that. Okay, so here we can switch on what kind of token we have, or operator. So yeah, parsing this is pretty similar to parsing infix operators. Well, I mean, it's exactly the same. At least I think it is. We'll see if it works. We just compare the binding powers. That was the whole point of them. But we will have special like parsing cases, because obviously these have to be parsed. They're not just operators. So for example, if it's the call, we parse function call. For p. And otherwise it could be an index. I like an expression again. And then we can continue here. Okay, so we can do those parse functions now. So here we're expecting the parentheses, the left parenthesis, right? The paren. And then just like all of our like other list-based like parsing things, we're just going to copy. Yeah, sorry. We have to do our comma check again. I feel like we should move that into a procedure. Just 2 lines. So call expression again, just to do this. And if we wanted to, we can obviously put commas with other expressions. And then the index expression is, we'll just write it on its own. Expression. Sounds good. Seems legit. So now I think I would still expect this to fail at comma, because I don't think we've handled like array initializations, but it should be able to parse through here if we haven't made any crazy typos. Right, yeah. Feels like we're looping forever. So where are we looping? Maybe where we're looping forever. Oh, we do have to add a break over here. Unexpected token, comma. I'm not going to worry about the precedence for now. I'll worry about that once we can actually see the tree. All that matters now is that we're actually parsing it. The precedence doesn't really matter because we have it set up. We can just adjust the precedence and the associativity later on. But for arrays, I wonder if we should make a new syntax for array initialization, or if we should try to peek and see if this, but the reason that I had this up here was because this is a valid array initialization too. So how do we know that we shouldn't be looking for a type? I guess we can just use our statement boundary. So if it has commas, yeah, I don't really like how that, I don't like that. It might be what we do for now anyway. It's like Zig and Odin, because Odin, I think you initialize the arrays pretty similarly as in Zig. It's like this. So you can parse it as a type, and then you can peek at the next token, and if it's this curly brace, you know that it's actually not just a type, it's a type with the array initialization. And I guess they do the same thing for structs. So maybe we can do that for structs. Sorry, just thinking about, I think we're just going to steal their syntax. I'm not really trying to make a particularly unique looking language here. But yeah, we're stealing it. That's how you do an array. Slice would just be like this. And then let slice type. And then let an array type. So this is what we're going to be trying to parse here. So we can just do an if. Early. Again, we're just going to use p. P. Equals not L curly. No, it's P actually. Yeah, it contains P. Let's make a function to parse an expression list. Limited. Never talk about tempo time. This will be 4. Parse an expression list P delimited by the right parenthesis. I think I messed that up. Whoops, that was not right. This is not an expression list. I was looking for call here. Expression list. Okay. For our slice, let's get back to what we were actually working on. Expect the curly brace, parse an expression list. think that's it. And now this is actually invalid. This is not how you would declare this. You would have to do like that. That should work. Epics. What is that? 218. Which let token is it freaking out at? It would be really useful to know where where we were. How many of these do we get to parse? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And what was the error that it was giving us? Unexpected token, keyword let. Where do we get an unexpected token? What were we expecting? We were expecting a right parenthesis, and we found a let. Who is expecting a right parenthesis? Oh. Ha. Fantastic. So we made it all the way down to here. Before we do whiles, I want to see if we can do kind of something similar with what we did here to the structs to re-enable us. Do this. Or not to re-enable us, we were never allowed to do it in the first place. We can just do parse an expression, and then if the next token is the left curly, then parse it as a struct. And the only issue, I mean, I think we're still going to push it. Like, we're not going to do it for now. Because the issue again is you can just have a block of code after this and do statements. And then it would try to parse this as a struct body. And one way we could do that is to try to like mark this token, try to parse it as a struct body, and if it fails, say, oh, it must not be a struct body. But we're not going to implement it that way right now. So we're going to go back to this, and instead we're just going to do the while statement. let's save this. Describe. So where is our main expression handler? Primary expression? No, this isn't an expression. That's the thing. This is a statement. Right. And are we using this statement boundary thing anymore? We're not. Which is cool. I like that. First while. I don't like having all these functions thrown all over the place, but the way it is. I don't know how to order them. What am I talking about? I'm gonna throw these at the bottom. So we expect our keyword. So we're just gonna have one while loop. Yeah, it's just a while loop. It's not a for loop or anything, just while. We just parse an expression. Great. That's the condition, and then we parse a block. All right. Expected a left curly found a less than. Because we don't have a less than operator. So we'll add one. In fact, we'll let's look at our tokenizer and see what tokens we even have. I know we have less than. We have less than and greater than. And these have pretty low precedences. Oops, less than. Okay. So they're going to be 1. These are going to be 2. They don't really have sensitivity, I guess. Unexpected token and expression equal. Oh, look at this. We have a plus equal. So we don't have the silence here. Okay. Instead of looking at this as a statement, we are just going to treat this as another binary expression. Even though, like, I think I'm going to, like, it's not going to be legal to say, like, I equal, like, A equals B equals 2. Like, I don't think I'm going to have that as part of the syntax. We will allow it to be parsed. which means we just need to add some more operators. So we have the assign operator. Equal. What? It's first of all a right associative, in case we did actually want it to work properly. Does this have high precedence or low precedence? Low precedence. Yeah, because we want it to at least be lower than plus, right? Because it should be done first. So this becomes our new lowest. And this is again why I have these functions. This happen to adjust precedences is really annoying. But it's nice that they're like auto-calculated. So equal is right associative precedence of one. Technically, that's not what we had. We had plus equals, but we don't have a plus equal token yet. Let's just see if we can get this to run and fail at, I don't know where that failed from. It was expecting an equal and found the let. Oh, over here, because we don't have equal equals. All right, let's tokenize the rest of our operators. So we have equal, we'll have equal, equal, less than equal, greater than or equal, plus equal, dash equal, star equal, slash equal. Good enough for now. So these can all be treated like we did the dot curly, I think. Where's our equal? So we can say the con is equal, the state is dot equal, and then change this to be a continuous statement. Right, the reason we did this check up here, which hopefully I'm not making a mistake, was for this end of file check. But isn't it fine if we're at the end of file? Oh, no. Yeah, it should be fine. Because if we loop again in the continue, we get to end of file. We're just going to return the token. Let's not change that. We're working on a particular thing right now. And we're working on a lot of things. A lot of particular things. So states less than. Okay, let's go add our states. So we're in case equal. If C equals yeah, we never get here if it's end of file. After the first character of these like multi-character tokens. So it would just be an error, like we would have an error token. We'll test it afterwards. For now, copy this a bunch of times. Plus start slash. And then we need greater than and less than. I think that's all of them. Oh, yeah. It is duplicate because slash can be followed by slash or slash equal. Where is our slash check here? Maybe we need to rename this to comment. Also, what happens when we peek and we're at the end of file? I think we have to change the state equals slash. Hopefully this doesn't break our comments. Expected and equal found keyword left. Parser. Yeah, it might be because of our comments. Or else we part expect and equal. Yeah, just in the declaration. So let's edit this tokenizer. I think that we're messing up here with our states. So when we hit a slash, we continue in our slash state. If we're in a slash state, advance it, or repeat the second slash, so that our token go to the comment state. The comment state advances and if we're at a new line, What is happening here? What I think we're going to do, we have a test here for the tokenizer. Let's test it. Odin test. So maybe this is working fine. It seems like it kind of is. I have an idea. We'll just find out how far we parsed. Print ln, and we will do p.p.source up to p.t.position. Why did we expect an equal here? That is the struct. What? I'm so confused right now. Expected equal found let. The only place that we're expecting equal is here in the declaration. Oh. We're parsing an expression. This is the expression. This is getting, yeah. Okay, that makes sense now. Oh. What are we going to do to fix this? should we make assignment not an expression? I wonder, like, this sounds like pretty similar to how Go would parse, or like an issue that Go would have parsing. I wonder how they do it. Right, because they use colon equals for assignment. And then if you want to assign, but also you can and I don't know if you can just go like this or not. Or maybe you still have to do this, I don't know. Whoa. Why did I get that? Let's just ignore that for now. Let's pretend that's not a problem. Okay, ignoring problems, moving on. If statements, did we didn't do if statements, did we? Let's get rid of that slice. So this is, did I say if expressions? I meant statements. So if we parse the expression, then we parse the block, and now we need to check if there's a an else. Actually, I think it's going to be in the whole loop. So for keep key equals dot keyword else. Advance. I guess that's why we didn't use advanced before, because normally we just expect here. Advanced does the same thing. And now we need to do an if. So now we check if there's an if statement. So if P is an if, can we call parse if? I think we can. Yeah, and in fact, then this doesn't need to be uploaded. So if there's an else statement, we see if there's also an if statement. If there is, we parse it as an if. We don't have to break. Otherwise, we just parse the else. We might have to change this again when we're building the AST. This might not really work that well for AST building, but it should parse. Equal is not an operator. Oh, look at this. We never actually added all of our... We have equal. And we also need or and and. These expressions, they have pretty low. So and I'm pretty sure has higher precedence in most languages than or. But also pretty low precedence overall. Did we not do... Oh, it's keyword or. Keyword again. Yo, we are making so much progress here. So, return statement. So expect return keyword. I know. So this is this is another place where semicolons might be necessary, because where is our here? I mean, technically, yeah, no. I think it does need a semicolon. So here's some of the issues that I'm thinking of. What if this was just returned? How does it know that it's not returned plus an expression? We could use our statement boundary, and then we could add curly braces as well to things that are statement boundaries. Let's do that and call it a non-issue. Expressions never start. I guess that's, yeah, let's write that comment. First return. Expect the keyword return if at a statement boundary to return otherwise just parse an expression, right? The only time we wouldn't be at a statement boundary is if there was an expression following the return statement. And if you do return and then you have some random statement down here, I don't know, then yeah, we're going to return this. Even though it looks like it might be a return and then execute this statement. Always spelling things incorrectly. Did we just parse the whole file? Guys, I think we've parsed the whole file. Incredible. I'm sure there's like a million bugs in here. And since I haven't like written this grammar out or anything, I'm just like winging it. There's surely some inconsistencies going on here. Oh, we should probably add a comma. To this list. And also keyword return. The thing about return is return can be an expression. But yeah, return is an expression. What are you talking about? Where's my primary? Yeah, return is absolutely an expression. Let's go down to parse statement. is not a statement. So cool. So cool. I think we're going to stop here. We do fail here. Okay. I have to figure out what I want. Like I want to handle struct syntax a little bit better. But that's fine. And I do kind of want to write a fuzzer. I've never written a fuzzer, but I want to generate like random source files and try to parse them and see if they error out or not. Other than that, I think we have enough here to go into building. Like I said, I'm probably actually going to skip an AST. I've been reading up on like sea of nodes and stuff, and I'll probably just like follow that kind of approach and just generate nodes as we parse. To that end, I was kind of thinking about like a generic, almost like some kind of interface. I know Odin doesn't have interfaces like directly, but I have to look in to see if there's some way I can implement it, because I may want to make an implementation that does generate an AST and an implementation like as it's going through the parsing here, just to compare it to like building sea of nodes as well. So anyway, that's for tomorrow most likely, or whenever I work on this again. Should be tomorrow. But yeah, that will do it for now.